Hi. So today I'd like to talk to you about energy and momentum in special relativity. Now, in addition to modifying space and time, special relativity forces one to reconsider concepts of mass, momentum, and energy. If length is contracted and time is dilated, a calculation of momentum and energy also has to change because these quantities, of course, are dependent upon length and time, which you can see just by doing a little dimensional analysis. Now, we can rescue sort of conservation of energy and conservation of momentum if we redefine these concepts using the following equations. The total energy must be E is equal to gamma times mc squared, where gamma is the factor that we defined before, 1 over the square root of 1 minus v squared over c squared. M is the mass, and c is, of course, the speed of light. The kinetic energy can be redefined to gamma minus 1 times mc squared, and the momentum can be redefined to gamma times m times v, where v is the velocity. Now, of course, these quantities are defined in classical physics. Kinetic energy is defined as 1/2 mv squared, and p is equal to mv in classical physics. And these quantities are not wrong, but the relativistic energy and momentum equations will reduce to the classical definitions for slow speeds. Now, in older treatments of relativity, conservation of momentum was maintained by using a so-called relativistic mass called gamma m. You might see this definition sometimes still on the internet or if you read an older text. But today, mass is considered to be invariant, and that means it's independent of speed. So the mass of an object in all frames is considered to be the mass as measured by an observer at rest with respect to that object. And then mass, of course, according to the equation gamma mc squared, can be interchangeable with energy during a reaction. Now, in terms of units for mass, the SI unit is the kilogram, but sometimes that's not a very convenient unit when it comes to small particles. And it becomes more convenient to use either the atomic mass unit, often symbolized by a U, or in terms of the amount of equivalent energy that mass is used to. So 1 atomic mass unit is about 1.66 times 10 to the minus 27 kilograms. This is based upon the definition of the mass of 1 atom of carbon-12. So we just defined the mass of 1 atom of carbon-12 to be exactly 12 atomic mass units. We set that. Why did we choose that? Well, I think pretty much because we're arrogant and we think that we're really super important, and of course carbon is fundamental to life, so it's fundamental to us, so we defined our system of mass with respect to carbon-12. Mass can also be expressed in the amount of equivalent energy. So for example, for typical nuclei, you might see the unit MeV per c squared. Now M is, of course, mega, and eV for electron volts, and then c you're dividing out by the speed of light squared. So from the equation E is equal to mc squared, which is the rest energy, which I'll get to in just a second, you can figure out what the mass is. It would be energy over c squared, and that's why we have those units, MeV, units of energy, divided by c squared. Okay? Now, 1 atomic mass unit is equivalent to 931.494 MeV per c squared. Now, you can use the conversion. 1 electron volt is 1.6 times 10 to the minus 19 joules to put it in more familiar SI units. Now, it's important to realize that that c squared in the denominator MeV per c squared is not just a unit there. You really are dividing by c squared when you want to do that conversion. And to prove that, I'm going to convert from 931.494 MeV per c squared to kilograms, and then you can see that it's equivalent to 1 atomic mass unit. So if you start out 931.494 MeV per c squared, I'll put the c squared there in the denominator. 1 MeV is 10 to the 6th eV, and then 1 eV is 1.602 times 10 to the minus 19 joules. So if I multiply through by those conversions, then I end up with 1.492 times 10 to the minus 20 joules per c squared. And then for my final step, I divide by 3 times 10 to the 8th meters per second squared, and I end up at 1.66 times 10 to the minus 27 kilograms. Okay, and that's 1 atomic mass unit. So you really have to remember to divide by c squared when you're doing those conversions from MeV per c squared to the SI unit. Now here's some masses in various units. You can see here, like I said, we defined 12 atomic mass units to be the mass of one carbon-12 atom. Now, just to look at this notation here, of course, C is the symbol for carbon, 6 is the number of protons, and then 12 is the total number of nucleons in the nucleus, so you know that we have 6 protons and 6 neutrons, okay? Now, you might notice that if you look at the mass of a single proton or a single neutron, that mass is more than one atomic mass unit. What happens is, when those nucleons come together and form the nucleus, some of the mass energy from the protons and neutrons is converted into a binding energy that holds that nucleus together. So some total mass is lost there when you take those 6 protons and 6 neutrons and combine them into carbon-12, you can see. Otherwise, the value would be greater than 12, right? And then that amount of energy binds the nucleus together, and it's called the binding energy. Okay. You can also see that the electron has a mass that's more than 1,000 times smaller than either the proton or the neutron by looking at this chart. Let's talk a little bit about how to do some momentum calculations. I figure an example is worth about 10,000 words here, so I'm going to do one for you. Muons in our upper atmosphere are known to travel at about 0.994 c, or 99.4% of the speed of light. Their mass is 105.66 MeV per c squared. So find the momentum of a muon in the upper atmosphere. Well, we're going to need to plug into the equation P is equal to gamma mv. So first I need to solve for what gamma is. So gamma is equal to 1 over the square root of 1 minus v squared over c squared. So that is 1 over the square root of 1 minus 0.994 squared, and that gives me a gamma of 9.14. So now I plug in 9.14 times the mass, which is 105.66 MeV per c squared, times the speed, which is 0.994 c. And this will give me the magnitude of my momentum. When I multiply those things together, you can see that the c squared in the denominator here cancels out with the c that multiplies the 0.994 up top. And so then when I multiply the numbers together, I get 960.2, and now my units are here, MeV per c. Now, in some of the problems that you'll do for special relativity, they'll leave the momentum in those units, MeV per c. But of course, you can convert that into the typical SI units of kilograms meters per second if you'd like to. So here I show you how to do that. 960.2 MeV per c. Yet again, you're multiplying by 10 to the 6th eV and 1 MeV. And you're converting here, 1 eV is 1.602 times 10 to the minus 19 joules. And then finally, c is equal to 3 times 10 to the 8th meters per second, and you have to divide by that. When you do that, you get 5.13 times 10 to the minus 19 kilograms meters per second. Let's discuss the kinetic energy and the rest energy. Now, the definition of kinetic energy requires modification in relativistic mechanics. You can't use 1/2 mv squared like you can in classical. Instead, what we do is we take the equation for the total energy, gamma mc squared, and subtract off what's known as the rest energy, or mc squared. Now, this is Einstein's famous equation. You probably heard about it long before this class, but it's simply the energy that an object has just because it has mass. So if you subtract the rest energy from the total energy, then that leaves you with the kinetic energy. You'll prove, in fact, that the classical kinetic energy equation comes out of this equation, gamma minus 1 mc squared, for homework. Now, the term mc squared is called the rest energy of the object, and it's independent of its speed. So the consequences of this are a particle has energy by virtue of just its mass alone, and then that total energy is the sum of the kinetic and the rest. And then that total energy, gamma mc squared, depends upon both its speed and its rest energy. Now, this E is equal to mc squared, let's talk about that for just a second. A very small amount of mass corresponds to an enormous amount of rest energy. And that's because you're taking a very big number, the speed of light, 3 times 10 to the 8th, and squaring it, okay? So the energy from nuclear weapons, for example, comes from either fission or fusion. Now, during these processes, some of the binding energy of the parent nuclei is released. Remember, we talked about the binding energy before. It's the mass energy that's been converted from the constituent proton and neutron that make up your nucleus. Nuclear weapons actually release so much energy that their yield is typically measured in equivalence to the explosion of tons of TNT or dynamite. 1 ton of TNT, by the way, has about 4.18 times 10 to the 9th joules of energy. Now, if you want to put some numbers to it, the bomb that was dropped on Nagasaki in World War II was a 20 kiloton warhead. If you do the conversion from kilotons to joules, that corresponds to 84 terajoules of energy. Now, you might not remember right off the top of your head what the heck a terajoule is. Tera stands for 10 to the 12th. If you rearrange and solve E is equal to mc squared for m, you get m is equal to E over c squared. So that kind of begs the question, how much mass was actually converted there in that explosion? How much mass does it take to make 84 terajoules? Well, 84 times 10 to the 12th divided by c squared, which is 9 times 10 to the 16th, gives you 0.00093 kilograms. So the explosion that leveled Nagasaki, pictured here on the right a few months after the bomb was dropped, converted less than 1 gram of mass. A little hard to top that, but I'll keep going. We can take the kinetic energy that we get from the relativistic equation, gamma minus 1 mc squared, and use it in the work kinetic energy theorem. Now, you might remember the work kinetic energy theorem from an earlier physics class. It basically just states that if you do work on an object and that results in the change of the kinetic energy of the object, then you can set the sum of the works on the object equal to that change in kinetic energy, which I've shown here. Work is equal to the change in kinetic energy, which is equal to gamma minus 1 mc squared. Now, you might say, what work would I might see in a typical problem in special relativity? Well, particle accelerators are often used, and in that case, you're going to be accelerating charged particles with very high voltages. Now, from introductory physics, you might remember that the work done when accelerating a charged particle q through some voltage delta v is equal to charge times the voltage, q delta v. And then you would set that equal to gamma minus 1 mc squared. Now, if you get nothing else out of this class, maybe you should remember what the definition of an electron volt is. Remember, the conversion for an electron volt is 1 electron volt is 1.602 times 10 to the minus 19 joules. Now remember, the charge on an electron, the fundamental charge E, is 1.602 times 10 to the minus 19 coulombs. So 1 electron volt is the energy that an electron has when traveling through 1 volt, basically. So if you multiply the charge in the electron, 1.602 times 10 to the minus 19 coulombs times 1 volt, you get 1 electron volt, 1.602 times 10 to the minus 19 joules. We did this on purpose, okay? This was on purpose. And the reason being that when you accelerate particles through a voltage, then you can basically just rewrite the energy from the voltage that you use. So I know that if I accelerated an electron through 20,000 volts, that its energy is 20,000 electron volts. Done and done. Now, this convenient system of units may have come from the ideas proposed by George Johnstone Stoney. He was an Anglo-Irish physicist, and he made significant contributions to cosmic theory, physics, and the theory of gases. He estimated the number of molecules in a millimeter cubed of gas at room temperature and pressure from data from the kinetic theory of gases, but maybe his most important scientific work was the conception and calculation of the magnitude of the atom of electricity. And in 1891, he proposed the term electron to describe the fundamental unit of electric charge. And his contributions to research in this area laid the foundation for the eventual discovery of the electron by J.J. Thomson in 1897. So he actually developed a system of units known as Stoney units and proposed them in 1881. And they're the first historical example of natural units where the fundamental constants like E, C, gravitational constant are all set to 1. Now, we're not going to take all of this because the units in Stoney units actually got a little nuts, maybe a little complex for this course. But we can just sort of consider the charge on an electron as 1 and accelerating through a voltage of 20,000 volts and multiply that by that, and you get 20,000 eV for the energy. So if you'd like to think about it, maybe you have Stoney to thank for that idea. Okay, let me do another example problem for you using these ideas of relativistic kinetic energy. So here's an example problem. Physicists at the Stanford Linear Accelerator bombarded 9 GeV electrons head-on with 3.1 GeV positrons to create B mesons and anti-B mesons. So what speeds did the electron and the positron have when they collided? So if you're thinking to yourself, what the heck's a positron, okay, then the positron is the antiparticle to the electron. Now we're going to cover antiparticles more as we go on in this course, but for now suffice it to say that an antiparticle has the same mass but an opposite charge to the corresponding particle. So a positron, for example, would still have the mass of an electron, 9.11 times 10 to the minus 31 kilograms, but instead of minus E of charge, minus 1.602 times 10 to the minus 19 coulombs, it would have plus 1.602 times 10 to the minus 19 coulombs. Now also note, and this is really important for when you're getting ready to do your homework, when problems cite the energies of particles in this way, 9.1 GeV and 3.1 GeV, what they usually mean is that that's the kinetic energy of the particle. Okay, so here 9 and 3.1 GeV, we're assuming that those are going to be the kinetic energies of the electron and the positron respectively. So let me work this problem. The rest mass of an electron and a positron you can look up in any table you'd like. I'm going to use the MeV per c squared units because it's more convenient for the problem in this case. So the rest mass of an electron and the positron is 0.511 MeV per c squared. Now let's solve. The kinetic energy is equal to gamma minus 1 mc squared, which is 9 GeV for the electron. So that's 9 times 10 to the 9th eV, and then I set that equal to gamma minus 1 times the mass, which is 0.511 times 10 to the 6th eV per c squared times c squared. Now those c squareds cancel out, and then I can make a ratio of the kinetic energy to the rest mass energy, and I get gamma from that, and gamma is equal to 17,614. Now I set that equal to 1 over the square root of 1 minus v squared over c squared, square both sides, go through a little bit of algebra, and I can solve for my speed. So the speed of the electron is 0.999999998, so that's 8 nines and then an 8 c, okay, for the electron. So it's going super close to the speed of light. Now I can also go through the same process solving for the speed of the positron. And if I do that, I set the energy equal to, kinetic energy equal to 3.1 times 10 to the 9th eV, repeat the process, I get gamma is 6,068, and V is equal to 0.999999998 C. Okay, so 7 nines and then an 8 for that positron, so really super close to the speed of light. Now, I'd like to bring your attention to something else about this example, and that's that this is the first case, I think, for this course that we're considering the idea that you can take less massive particles, like electrons and positrons, and then accelerate them to super high speeds close to the speed of light and smash them together. And then that kinetic energy is going to be converted into another form of energy. Remember, energy is not created or destroyed, but it can be exchanged between one form and another. In this case, the exchange of the kinetic energy goes into rest mass energy. So you're creating more massive particles in this case from less massive particles. Let's go through this. The initial mass of the system is 2 times 0.511 MeV per c squared because you've got both an electron and a positron, and that equals 1.022 MeV per c squared. So that's your initial mass. Your final mass is the B and anti-B meson. Now, the B and the anti-B meson have masses of 5,279.15 MeV per c squared, and there are 2 of them, and so that means that your total rest mass after the collision is over is 10,558.3 MeV per c squared. Okay, so if you compare those 2 numbers, you can see that the mass here has increased by over a factor of 10 because of that reaction. In fact, you'll even have some kinetic energy left over for those B mesons after it's all over. You started off with 9 plus 3.1 GeV of energy, and so now you have 12,100 MeV of energy initially, and your rest energy only accounts for 10,558 MeV, and that leaves 1,542 MeV of energy for kinetic energy to go into those mesons after it's over. Okay? All right. So if that doesn't blow your mind, I really don't know what would. And I hope you enjoyed that, and I'll see you in class.